An object is launched along the x-axis from the origin with an initial velocity of 5 meters per second. The subsequent motion can be modelled by the equation d2x by dt squared plus dx by dt minus 6x equals 0. Find the particular solution for x in terms of t, where x is measured in meters and t is measured in seconds. This is a second order homogeneous differential equation. Now we're told x is in meters and t is in seconds. X is the displacement and t is the time. Actual real physical quantities with units. Now if you look at page number 39 in the course specifications, they have got an expression that we are asked to think about during the course. And that expression is this: a d2y by dx squared plus b dy by dx plus cy is equal to 0. Now that expression is all very well, and all of those values in there are dimensionless numbers. So we don't need to think about displacements in time. We just carry on with the solution without thinking about that. But this is a physics problem now. A very real physics problem with actual physical quantities. So we have to make sure our units are consistent. Now, if we look at our expression again, the first part of that expression on the left hand side, we're asked to differentiate x as a function of time twice. That gives you an acceleration. We're then asked to differentiate x, which is displacement, as a function of time once, which is a velocity. But you cannot add a velocity to an acceleration. So our units for all three parts of that expression have to be the same, which will be meters. So in order for those to be meters, a and b in our expression aren't just equal to 1, they've got actual units. A is equal to 1 second squared and b is equal to 1 second. If you multiply seconds squared to an acceleration, you get meters. If you multiply seconds to meters per second, you get meters. So everything's in meters, and we're ready to proceed with the question. That gets that detail out of the way. Now you won't need to mention that during the exam. You won't even have to think about that. But when you're doing these things actually in mechanics and physics, well, you have to be aware of the units involved. Otherwise, again, we're in a world of vagueness. If you look back to question number 4, there was another differential equation, second order differential equation we came across when we were working with simple harmonic motion, and that was d2x by dt squared is equal to negative omega squared times x. And we noticed that sin omega t or cos omega t satisfied that. But those two expressions will not work here. Try it and see. So what does work then? Well, you could be there all day putting expressions in, hoping for the best. But that's not the way we do it. Make an intelligent guess. Now how we proceed is this. Let's take the simplest, possiblest differential equation in terms of dimensionless quantities. And that would dy by dx is equal to y. Only thing that satisfies that is the exponential function. Because when you differentiate the exponential function, you get back to the exponential function. Differentiate it twice, you get back to it again, as indicated in the front of our exam paper. It's giving that information there. Now, since the exponential function repeats itself after subsequent differentiations, it's going to fit into the differential equation that we are asked to solve. So we're going to choose for x of t to be e to the lambda t, where lambda has units of per second. See if you can work out why that's necessary. And e to the lambda t has got units of meters as per the question. Now, our overall solution is going to look like this. X of t is equal to capital A, where A is a constant, times e to the lambda subscript 1 times t, plus b, which is a constant, e to the lambda 2 subscript 2 times t. Our solution will look something like that. So our job now is to find the two lambdas, lambda 1 and lambda 2, and to use the initial conditions to find what constants a and b are. Now to do that is actually quite simple now, because what we do now, we take our x of t, e to the lambda t, and we insert it into our differential equation, and we just do what we're asked to do. For example, we're asked to differentiate it twice, then we're asked to differentiate it once, then we're asked to take away 6 times the displacement function. Then when we do that, we find ourselves we've got a quadratic equation, and when we solve our quadratic equation, we get our 2 lambdas, lambdas 1 and lambda 2, and we set that into our final solution. Then to find A and B, all we have to do is use our initial conditions. We're told that at t equals 0, the displacement is equal to 0, and we're also told that at t equals 0, the initial velocity is 5 meters per second. And that's enough information, as we shall see, to find out what A and B are. Then we can write down our complete solution to our problem. Let's go ahead and do that. And if you've got time at the end of the exam, you can put that displacement function into the formula to see if you got it right. I'm going to stay with it for a second longer though. Suppose we take our velocity function and we differentiate it again. Then we get the acceleration function, which is 4e to the 2t, take away 9e to the minus 3t. Now at t equals 0, the acceleration is negative. And at t equals 0, the velocity on the other hand is positive, therefore the opposite sign. Now these are vectors, remember. Displacement, velocity and acceleration are all vectors. So if you've got a velocity and acceleration and the opposite signs, necessarily the velocity of the body is slowing down. But we are told in the question the body was launched. Now no body that's launched, with my understanding of the term, ever slows down. So they'll need to word that question differently. They will need to say, well, this doesn't model the motion of an object after t is equal to 0 seconds. But they would have to avoid using the word launched, because if you look at the 3 graphs, the 3 graphs verify this. I've drew them up to 1 second because it's unlikely that something real on Earth will have a rapid acceleration like this for any great length of time. You can see the 3 graphs. So the word launched here is an appropriate in the question, but it never is an interesting question, and it can show, and there you are. Those are the displacements, that's the acceleration, and that's the velocity of that function after or during the 1 second. Any questions about this? Just ask. If you like it, give it a like. And question number 6 on this paper will be appearing shortly, as well as questions on other physics papers like the advanced higher, the higher, or the standard grade, or the national 5, I should say. Thank you very much for watching the Young Scottish Physicist.